Morning, everybody. Welcome to the Linux kernel hidden inside Windows 10. This is Mandalay Bay EF, in case you're in the wrong room. Have the pleasure of introducing Alex Ionesco. Before we begin, a little housekeeping. Please stop by the business hall located in Bayside AB during the day and for the welcome reception from 1730 to 1900 tonight. The Black Hall Arsenal is on the Palm Foyer on level 3. Join us for the Pony Awards as well in Mandalay Bay BCD at 1830. Also, as usual, please put your phones on vibrate. We don't like to hear your phone ringing. Thanks, Alex. Good luck.
Thank you. All right, thanks everyone. So welcome to the Linux kernel hidden inside Windows 10. A little brief by myself. Currently VP EDR strategy at CrowdStrike, security startup, as probably some of you know. Worked at Apple before that on the core platform team, helping get iOS ported basically from OS 10. And most of you probably know me as is the co-author of the Windows Internals book series, which I'm happy to say, by the way, finally has a 7th edition that someone will be publishing. So for those of you who are waiting for that, apparently it's going to happen. So most of my knowledge in Windows comes from what I've been doing for the last 15 years, which is just reversing Windows with IDA and other tools before that. I was main developer of ReactOS, so an open source implementation of Windows. And this has pretty much been my passion ever since, taking apart Windows and looking at what's inside it and what's hiding under the hood. And as every new version of Windows comes out, what other new things are hiding under the hood. And obviously, as the talk title suggests, there's a pretty interesting thing hiding under the hood this time. So we'll see kind of how all that works. One little caveat, I guess. Someone posted out there actually, spoiler alert, there isn't any Windows Linux kernel in the Windows kernel. So I guess I was wrong. All my research was incorrect. So you can go. Apparently, there's nothing there. But if you think there is, you maybe want to stick around, and we'll see what's actually in there. So basically, we're going to talk about some NT-kernel concepts, minimal and pico processes. Quickly talk about what exactly is a minimal process and what's a pico process. And then how do you become a pico provider for a pico process? Very quick kind of intro with some NT there. And then we're actually going to talk about the Linux subsystem. The Linux subsystem has a few components, which I'll talk about. One of which is LX Core, which is going to be the kernel mode driver. And the other one's LXSS Manager, which is the actual service. So we'll talk about some of the functionalities, some of the interfaces that the driver and the service has, as well as some attack surfaces that exist inside of it. LXSS, the Linux subsystem, also has an interesting IPC mechanism. It's not exposed. I mean, none of this is really exposed. But we'll talk about kind of how Windows processes and Linux processes can actually talk to each other. So that's a good warning. Just turn that on. All right. So we'll see how Windows and Linux processes can talk to each other and how Microsoft kind of implemented that functionality. And then we'll actually talk about probably what most of you are here for, the security design considerations of all this. So first of all, when I first encountered the Linux subsystem many months ago, almost more than a year ago now, there were a number of things that were very scary about it. And I got the chance to approach Microsoft about it and kind of work with them, giving them some ideas on how they can improve things, and happy to report most of the issues have been fixed by now. But there are some important kind of environmental things you need to be aware of. As a sysadmin, as a developer of endpoint security products, we're going to see there's some very interesting things about these processes and kind of how they exist in the environment that they run in. If we have time, I'll talk about some very brief forensics you can do, like, for example, how you can use the debug viewer to see some of the internals, how you can use WinBack to see some of the internals. And hopefully we'll get a chance to show a few demos. I've got a demo of just kind of a nice thing is just how you can build Linux apps with Visual Studio with the subsystem, which is just kind of for fun. But a more kind of interesting demo is I've actually built a Linux application and a Windows client that talk to each other using the undocumented IPC mechanisms. So you can kind of just see how that works. And also how you can launch a Linux app without using the bash environment that they give you, which obviously is interesting because it means that if we had an O day today in Windows 10 anniversary update, you could, instead of popping calc, you might be able to pop a bash prompt, and that'd be pretty funny, right? So we'll do a few demos there, and then I'll conclude and have time for questions. If there isn't any time for questions, because I've gone over like I almost always do, since there's a coffee break, I'll be around, and you can ask me questions throughout the conference, and you can just harangue me when you find me. All right, so let's get started. Talk a little bit about this idea of a pico process and of a minimal process. So the idea of a minimal process actually showed up in Windows 8.1. it wasn't clear what it was going to be used for at that time. You have to remember that a lot of this stuff we're seeing obviously was built over years, and little pieces of it kind of leaked out over time. But a minimal process is essentially a Windows process that has no address space created by default. So there's no PEB, which is a standard thing all Windows apps have. There's no NTDLL, which is a standard DLL all Windows applications must have. There's no key user shared data, which is another structure everyone has to have. There's no handle table either. So they're very kind of bizarre processes. Like the name implies, minimal, they don't have the things you would expect to find. And the only way you can kind of tell that a process is minimal, obviously other than everything's missing, is there's a flag in the process called minimal that's set to true. Now, so you create threads inside these minimal processes. The threads have no tab, they have no stat that gets created, and they don't have the standard user mode context that gets created either. And again, there's no real way to tell them apart other than, again, they have a flag called minimal set to true themselves. So how do you get these minimal processes? Well, in Redstone 1, which was the code name for the anniversary build of Windows that came out yesterday, there's the ntCreateProcessEx function lets you pass a flag to create minimal processes. But it's only exposed for kernel mode. So from user mode, you can't create minimal processes, at least not today. But in the new Windows 10 build, if you look at Task Manager, for example, you're going to see a process called memory compression, which implements some of the new memory compression technology they've had in Windows 10. That's a minimal process. You're going to see something called secure system. If you enable virtualization-based security, which I talked about at Black Hat last year, that again is a minimal process. So they're basically these empty processes with nothing in them, but they still have threads that get scheduled. They still have memory, and they can still execute stuff inside, but just kind of not your usual user mode environment. On top of these minimal processes, you then have Pico processes. And what a Pico process is a minimal process that has a Pico provider. And essentially what makes them Pico processes versus just minimal processes is there's a flag or a pointer called Pico context, and Pico context not being null implies this is a Pico process. And then threads inside a Pico process become Pico threads. So what does it mean to be a Pico process or a Pico thread? Well, for example, if you make a system call, you're going to be rerouted to a Pico provider. If someone wants a stack trace, it gets rerouted to the Pico provider. If you get an exception or a page fault, it gets rerouted to a Pico provider. If someone wants to know what the name of the process is, you guessed it, rerouted to Pico provider. If someone tries to open a handle to this process or the thread, Pico provider says yes or no. And finally, when a Pico process dies or a Pico thread dies, once again, the Pico provider is notified. So basically, all these kind of essential execution aspects of a thread get subsumed by a Pico provider instead of by the normal native functionality that the Windows kernel provides. So you're not doing NT system calls, you're not having NT exceptions anymore, you're not having NT stacks. Whatever the Pico provider is providing is what these processes end up seeing. So basically, Pico providers are custom kernel mode drivers that allow you to implement callbacks so that you can then kind of host a Pico process and provide all the functionality that's going to need. And this is basically the implementation of a Microsoft research project that went on for many, many years called Drawbridge. And so that project, matured from a research project to a productized implementation in the anniversary update. And so the kernel exposes a function, ps register Pico provider, and now you can register a Pico provider by providing the callbacks that the kernel is going to call. And then you get some callbacks as well so that you can now create Pico processes, create Pico threads, etc. However, the key is this API will only work if this flag, PSP Pico registration disabled, is set to false. So if it's set to true, then you cannot register a Pico provider. And before loading any third-party drivers whatsoever, whether you're an ELAM driver or a bootstart driver, that variable is already set to true. So the only thing that can call the API early enough is a Microsoft built-in driver. And so right now there's only one of those, and there's only one Pico provider. And of course, you guessed that it's going to be the Linux driver that actually uses this functionality. Now, once you're a Pico provider, you get access to some APIs. So there's some things you can do on a system. For example, you can create Pico processes and threads. You can associate and get a Pico context associated with these things. You can define the starting CPU context of these things. You can suspend them and resume them. You can kill them, obviously. And you can also configure their FS and GS segments. So basically, this lets you create and control these types of processes, which you then essentially manage. So this is a very nice diagram that actually Microsoft published on their blog. So copyright and kudos to them. And basically what you see here is an NT process is just a normal Windows process with all the NT things you're probably familiar with. A minimal process has none of that inside it. And then a pico process is basically a minimal process which has nothing inside it either, but has a pico provider taking care of all its exceptions, all of its system calls, and everything else. So it's an extension of the idea of a minimal process. So that's basically the internal kind of functionality that makes all this work. Now, you might be wondering, can someone register their own pico provider? Can someone hook pico providers? Because obviously, if these things can hook all the system calls and do everything they want, what prevents a bad guy from doing that as well? So pico providers actually register with PatchGuard, which is the Microsoft anti-hooking technology in the kernel. So PatchGuard will actually protect the pico provider, will actually protect the system calls inside the pico provider as well. So in the Linux case, it means that all of Linux's system calls are actually going to be protected by PatchGuard, which is pretty cool. Now, if you try to register a fake provider, PatchGuard will catch you. If you try to patch that Boolean that says, oh, no, registrations are enabled now, PatchGuard will crash you. If you turn the Boolean on and then turn it off, PatchGuard will crash you. And if you try to actually hook the pico provider callbacks that the kernel saves, those are protected by PatchGuard as well. So there's a lot of kind of security Microsoft put here to make sure no one is showing up with their own pico provider to basically hook your applications and do bad things to them. So people have to find ways around the PatchGuard implementation if they want to do that. So how does this fit into the kind of the Windows subsystem for Linux, the WSL component, or I like to call it the Linux subsystem? Well, basically you have a pico provider driver. It's instantiated by lxss.sys, but the actual provider is lxcore.sys, so linuxcore.sys. And that's really what provides the kernel mode implementation of a Linux-compatible kernel ABI and API. So there isn't the Linux kernel. There's no GPL code here. It's basically a Linux-compatible ABI and API. So all the system calls are there, the environment is there, but there's no code that was shared within the Linux Foundation or the GPL or anything like that. It's completely clean. And it also provides a Windows interface to manage these Windows subsystem Linux instances. So it has a device object, device LXSS, and that allows basically command and control the driver and various things you can do to it. It also provides a bus idea, and the bus is basically what allows the Windows subsystem for Linux instances to communicate with the NT world. The driver also implements VFS, so you get the full virtual file system implementation that Linux has. You get inodes, and there's even a device inode on the Linux side to talk to this. So the Windows side can open /device/lxss, which is the NT name, and then we're going to see later, there's a /dev inode, which Linux can use, which is a Linux name. In user mode, you then have a management service, LXSS manager, and this then provides a COM interface around the driver. So you don't talk to the driver directly, you use COM over RPC to talk to the Linux subsystem manager, and then it uses ioctls and ERPs to talk to the driver. Now, what is this running in user mode and in the Linux environment? Obviously, if you have Linux, you need all your Linux binaries. You need bash, you need grep, you need wget. Where are all those coming from? You essentially get a user mode Ubuntu 14 environment. So when you first install this, you get the ISO from Ubuntu directly, and it just lays down a file system with all the standard binaries you can have in an Ubuntu 14 distribution. The key thing is that Ubuntu, though, has an upstart or systemd process, right? That's your init daemon on most Linux systems. Well, Microsoft had to write one custom piece of code here, which is their own init daemon. So everything else on this file system is basically directly from Ubuntu, unmodified. But there's a custom init daemon, which you're going to see actually kind of makes it all work, because that init daemon needs to know it's not really running under the Linux kernel, but it's running under kind of a wrapper or a compatible Windows implementation of that kernel. You then have two simple processes, lxrun.exe, which is how you install, uninstall, update, and service the subsystem. And you have a launcher service, which is essentially bash.exe. And then bash.exe spawns instances of bash or other things, as we're going to see by talking to the LXSS manager. And lxrun will also talk about how it kind of provides all that management and installation. So we're going to go over these components a little bit more detail. That being said, that's kind of the big scary picture, which no one will be able to read right now on the slides, which will be posted online, obviously. So that's basically kind of how the whole system works, and we'll go and talk about some of these components. Again, this is tiny, I know. When you get the slides, it'll look a bit better, but just architectural show off. All right, so let's talk about the LX core side, and then kind of go a little bit deeper into how it functions. So first of all, it's a driver, right? It runs in kernel mode, so it's ring 0. It's about 800 kilobytes. So it's a very large piece of ring 0 code, obviously re-implementing the entire kernel ABI here. Now, in some cases, the implementations of the Linux API are written from scratch. So for example, the pipe implementation is a from-scratch implementation of Linux pipes. In other cases, we're just kind of wrapping something that the NT kernel already provides. For example, scheduling. There isn't a custom scheduler that's like a Linux-specific scheduler in any way. You basically just wrap all schedule APIs to the NT scheduler, and the NT scheduler takes care of all that's work. In other cases, you get a mix. For example, the file system. Well, the file system is still NTFS. This still installs an NTFS kind of directory and lays out the files on your machine. But on top of NTFS, they built VFS. They've built the idea of inodes. They've built the VFS-style caching of inodes and directory entries. And they've built, TempFS and other emulated things. And so sometimes you get a mix, just like in the networking scenario as well, where ultimately the networking is done by the Windows TCP IP stack, but there's a whole BSD socket emulation layer or wrapper layer on top of that. And basically, when they did one or the other, essentially it had to do with compatibility. For example, NT pipes, NT has a named pipe file system, NPFS. NT pipes have slight differences from Linux pipes. So if you just took Linux pipes and implemented them on top of NPFS, things wouldn't be that compatible. So they had to do that from scratch. Meanwhile, scheduling, well, the scheduling algorithms are highly internal to OSs anyway. Linux changes theirs, every major build. So things aren't that dependent on the scheduler. In other cases, they had to do things that were close enough. Like they didn't want to write, full support for real XFS, with real inodes on top of that. So instead they took NTFS, they kind of put VFS on top of it, using things like alternate direct data streams or extended attributes, and it works close enough. Like there's some issues with like case sensitivity and symlinks pointing to the wrong partition and weird things like that, but it's close enough for now and they'll keep kind of improving on it. And it's also important to remember that NT originally had a POSIX subsystem. So the idea of case sensitivity, the idea of devices that aren't just drive letters, the fact that there were extended attributes in ADS and NTFS, a lot of the original design decisions done by Dave Cutler and his team back in the 80s and 90s paid off to basically make this work. Because if the Windows kernel was not case sensitive, it would have been a lot harder to kind of bring this into light today. You can also customize the driver a little bit. So there's some registry keys. This is mostly for reference that allow you to set up some tracing and some additional features of the subsystem. This is probably intended for testing, but it's useful for forensics as well. So you'll have this on the slide once these are released. So obviously one of the most important things that the subsystem can do is provide the system call interface that Linux applications are going to need. Now Microsoft actually has the full official list on their release notes page. So actually they listed in every build what system calls they added, which is pretty nice of them to do. So today, as of the release build which came out yesterday, there's 216 system calls, Linux system calls. They're implemented by LXP sysdispatch. There's support for ptrace, which is really nice. You can enable certain debugging features like have a breakpoint if a system call fails. And you can also enable system call tracing. And if we have time, I'll show you that, where you basically set up a few variables in the kernel or in the registry, and then in debug view, you can see every single system call that's being made, which is really good. It's kind of like having a progmon for the Linux world. It's just traces, but it's better than nothing. So that's kind of one interface that it has. The other interface that it has, of course, is the file system, or VFS. So there's two main kind of file system groups that they implement. One of them is called volfs, and this is basically your Linux-facing partition. This is where you have support for Unix rights. You can chmod, chown, and this uses a lot of the NTFS alternate data stream support and extended attribute support to basically emulate or wrap some of the Linux file system specific things on top of NTFS. And so because of that, this file system or this directory on your file system isn't compatible with Win32. If you drag a Win32 file in there from Explorer, it's not going to have the right attributes. It's not going to have the right data streams. So the Linux system is not going to understand what to do with this. So there's a second file system model called DriveFS or DRVFS. And this actually is the Linux-facing system that implements or maps your Win32 drives. So by using Linux mount points, they actually mount your C drive, your D drive, whatever external USB drives you have. They mount them in the Linux world, and then you can actually interoperate with the files you have there. So you're not supposed to kind of touch the Linux side of things, but if you got your own files, the Linux subsystem can read from them and vice versa. So this is a real, one of the things that I often get asked is this is, all running on your host. It all has access to your file system. So there's no kind of emulation or VM around here. It's a real file system that it can access. And then on top of this, they also implement things like procfs, obviously. So you actually can go and, cat/proc/the PID and this will call the appropriate kernel APIs. There's tempfs, of course, which provides like the /dev, so you have actual devices that they implement. Now, they don't implement real device drivers in this environment, right? So you don't have access to your webcam, for example. You don't have access to your printer. You don't have access to USB or PCI devices other than the network, obviously mouse and the keyboard. So you have your input and output, but you don't have custom device drivers that you can talk to or that are mapped in any way, which is a good thing because the last thing you want is Windows drivers suddenly talking to Linux processes. And there's sysfs is there, of course. So the file system obviously is a big piece and another kind of attack surface behind this. And Microsoft, again, on their blog has a really good picture that they put up, which basically kind of shows you, there's your Linux application, there's LX core, all the system calls that are implemented by the system call layer, go down to VFS, and then there's your volfs, which is, again, your Linux environment, your drvfs, which is your Windows mount points, and then tempfs, procfs, sysfs, etc. All this then built on top of the NT-kernels, object manager, IO manager, and NTFS. So ultimately, the reads and the writes are still done by the NT-kernel when all this is said and done. So when this thing basically starts up, it's got a little LX core initialize function and basically registers itself as a Pico provider, sets up some event log tracing. So actually this is fully kind of plugged into the event log. And if you're familiar with ETW, you can enable it and see everything that it's doing. And then it just basically waits for ERPs. So it waits for IO request packets from user mode. So someone can come in and request the create, close, and cleanup to basically create instances or entities of the subsystem. There's ioctls, the device control to actually configure and set state and talk to the subsystem. And then there's read and writes, which are used by the IPC mechanism. So when this thing starts up, it creates this /device/LXSS device object. Now, on top of this device object, you have 5 different interfaces. You have a root bus interface, and this is how the Linux manager service creates new instances. Once you have an instance, you then get a device or file object for the bus instance interface. And every instance has a GUID, and so you now have a file object inside of this namespace to talk to specifically to that instance. And what's an instance is basically just a Linux session. So it's your init daemon, and then anything you create under that, under your kind of account token. Then you can obtain a client interface to the instance. So the instance can have multiple clients talking to it, and these clients can then basically set up IPC among themselves. So as the clients set up IPC, they're creating IPC server ports and IPC message ports. The model is very similar to ALPC, if you're familiar with that, or RPC in user mode. It's all custom and internal, but it's basically how instances can talk to Win32, and we'll see how the subsystem actually uses that internally. So the root bus basically has a single ioctl that the Linux manager calls, ioctl, ADSS, control, whatever. And this basically sets up an instance, and it creates the GUID, it mounts the file systems, it creates the job object, it passes the token, tells us what to map inside the mount points, and basically just defines what the instance is going to look like. Nothing starts yet. Once the instance is actually being created, then you get a handle to the instance, and then there's an ioctl there, set instance state, and the LXSS manager service starts the instance. Obviously, you can then update network path, update network cards, or map any paths that it needs. But once it starts the instance, then the init daemon actually starts up. So then you get init, and you're going to see init and process hacker or task manager, and then whatever is the process you want to launch after that, we're going to see it gets launched. So initially, an instance is just an instance of init, and then something's going to have to go and talk to that. Now, once an instance is created, you can have bus clients. So clients, again, are things that are talking to the instance, and a client can register a server. A client can also connect to a server. So the server side of a client that's a server will basically register a server. A client that's a client of that server will connect to it. There's some other things which I did not look at. I don't know if they're actually used, enlightened forks and file system callbacks. So I have no idea what these things are actually used for. I spent a long time reversing this, but I couldn't really see anything using those, so they may be things for the future. Now, once a instance is created, in the Linux world, you get a /dev LXSS. So this is something you can actually see in Bash, and this is basically how a Linux process can talk to the instance and become a client of it. And the idea here is on the Windows side, someone can use the Windows ioctl interface to register a service. On the Pico side, on the Linux side, someone can use the Linux device instance to connect to that service. And as we're going to see in the APC section, now you can have a Pico process or Linux process and a Windows process talking to each other. The key thing is that only the init daemon is actually allowed to talk to that. Now there's a registry key I'm going to show you later which lets you bypass that, but by default only init can actually talk to this instance and talk to the Windows world. But there are ways around that. So then the server and message ports are basically how a Pico or Linux process and a Windows process can talk to each other. And it allows two things. It allows raw data to be sent through read and write calls, and it allows marshalling and demarshalling as well. So there's some things you can marshal, there's some things you can demarshal, and I'll show you what those are. And then you can also associate events, and you can map memory as well. So one side can map memory, and the other side can map that other process memory. So you can have memory mappings between the Linux world and the Windows world. And we're going to talk a little bit more about that in the IPC section. So that's kind of what the kernel driver provides. And now take a look at some of the user side behind all of this. So LXSS Manager is the thing that provides the user mode service. And LXSS Manager is essentially a service that is in a service host. So it's going to be one of those svc host.exe processes. And inside of it, it's going to have a DLL, which is going to be LXSS Manager. Now, it runs as a protected process light, or PPL, at the Windows level. So if you're not familiar with PPLs, I've given talks on this, or you can read the blog or MSDN. But essentially, it's a very protected, as the name suggests, process that no one can really touch. And we're going to see in the security section why they made it a PPL. It then registers a COM class, LXSS user session, which then implements an interface called ILXSS session. So over COM, things can now talk to the LXSS manager. Now, it has one single interface, which is LXSS session. And with that interface, you can ask it to start a new instance, to get the current instance ID, to change the state of an instance, to get the state of an instance, or to initialize the file system for the first time when you first kind of install the thing and laid it down. Once you either get an instance or start an instance, you then get an ILXSS instance COM object, which you can then use to configure the instance, query and send information on the instance, register a server that is going to use the IPC mechanism we're going to see, or connect to a server. So the Linux side can actually have a server of its own that you connect to. And most importantly, perhaps, the ability to create a Linux process inside of this instance. So you can request the instance to actually create a process, and we're going to see what's actually going to do that work. Now, some of these COM objects and requests can be done from anyone. Like, for example, if you call create LX process, you don't have to be admin to do that. What's going to happen is you're going to get a Linux process that is going to have the same token as your user account. So if you're Alex and you create a Linux process, you're going to get an Alex Pico process from the kernel's point of view. The other things, like for example, registering a bus server, that you actually have to be admin for. So the COM calls are going to check your token and whether or not they allow you to do that. Who actually talks to this manager officially? It's not documented, so you shouldn't be just grabbing COM objects to this like I have. Two things, lxrun.exe and bash.exe. So these are the two Windows binaries that you get on the machine, which allow you to talk to the Linux manager, and then the Linux manager will then talk to the driver. So what do lxrun and bash do? lxrun is essentially what lets you create users in the Linux environment. It lets you install and uninstall the Linux environment, and it lets you service it and update it. All of this is done through command line options. So you can run lxrun/install, lxrun/uninstall, lxrun/set default user, etc. And internally, this basically has some classes that help you do that. The ironic thing here, the thing that makes sense, I guess, maybe not ironic, but I thought it was cute, is that all of these actions ultimately then launch Linux processes. So like if you call lxrun set default user, this basically launches user mod, ID, passdw, add group, del user, and add user. So it actually calls the Linux Pico binaries, launches them in an invisible instance to actually do that work. Similarly, if you actually do an update, well, what update actually does is it spins up an instance and just calls apt. And then it does an apt get updates for you. So this actually just launches the Linux apps behind your back. So you could actually have just yourself launched bash and done an apt update if you wanted to. But Windows users might not know how to update an Ubuntu environment. So lxrun basically acts as a bridge between what Windows admin might know how to do and what they might not know a Linux process requires. And then finally, bash. That's essentially your launcher. It has a single kind of function inside of it, and it uses that create LX process to let you launch anything you want. Now, normally when you launch bash, it looks like all it does is launch the bash prompt. But if you actually do bash-c, for example, and type another command in quotes, it's actually going to run that command. Just like in a real Linux system, if you use bash-c, it launches that other binary. What's interesting here, though, is that you're not going to get bash, which then will process the argument and then launch man. The bash.exe itself will understand what this means, and it'll just launch man directly. So if you use bash.exe-c, it creates the instance and launches whatever the kind of binary you put in there. So it doesn't actually, it's not going to be routed through bash. Versus in a real Linux system, if you use bash-c, bash is actually the thing that processes that, and then it launches the sub-process. So very simple thing here is just a launcher, and it just reads your registry to basically figure out what token should it use, not what token, but what Linux user it should use. So if I'm Alex and I've defined a Linux user called Bob, when I launch bash, it's going to say Bob in the Linux environment, because that's what I've configured it to. So basically it knows the UID and the GID that at installation time I configured, and then I can use lxrun to configure additional users and use standard commands in Linux to switch between the users, and so on and so forth. So those are the Windows-facing side of things. That's how you can kind of launch a prompt, talk to it, and that's who it talks to, and that's the driver that it talks to. But the key missing piece here is that there's something needed on the Linux side too. Because if I send a create bash request to the LXSS manager, how does the Linux manager in the Windows world know how to create a bash process in the Linux world? So what you then need is the init daemon. So an init daemon starts up whenever the instance gets started, and basically has a very simple initialization function called init entry. It closes every handle from 0 to 2048, kind of a weird defense mechanism. It opens /dev/k message. So if you're a Linux person, or almost any OS person that's not Windows, you probably know what that is. So that's your kernel log. And it duplicates that as in standard error. So any errors are basically going to go in k-message. And then it makes standard in and standard out be /dev null. So it doesn't have any standard in or standard out. And then it opens the handle /dev/lxss. So it becomes a bus client of its own instance. Then creates a symlink for resolve.conf. And then it tries to connect to a server. And it tries to connect to an IPC server called LXSS Manager. And that's what the LXSS Manager on the Windows side has created as an IPC server on the Linux side using the bus driver, the Linux driver that exists. It basically creates a listening server that can now receive, that can now send commands, to the init process and also receive responses from the init process. And then basically sets up some signal handlers, and then it sits in a loop, and it just calls read message from server. So it's just waiting for messages from LXSS Manager. Now what can LXSS Manager ask it to do? Very simple things. It can ask it to update the network information. So there's an API init update network info, and essentially this will update etc resolve.conf. You can update the time zone information, and basically this creates a symlink and sets up user share zone info Microsoft local time. If you update your host name, this then will call set host name, it'll call set domain name, and it's going to update etc host name and create an etc host file for you. So kind of these first three things make sure that the instance is up to date to Windows changes. So if you change the time zone in Windows, it changes in Linux. If you add a host name or change the host name in Windows, it happens on the Linux side as well. So this kind of keeps state synchronization between the Windows world and the Linux world. And then perhaps the most important thing it does is provide an API to create a process. So basically over that IPC channel, LXSS Manager can talk to the Linux process and ask it, please create a new process. And it's going to pass to the environment variables, it's going to pass to the command line, the working directory, the standard handles, and then init will call fork. After fork returns, you get a PID back, and then it's going to set up the UID, the GID, the environment variables for the home and the path, set up the session, the console session, duplicate any handles that it needs, and then call exec VPE and actually exec, right? So it's a standard fork exec, just like you would do in a Linux process. And then init now forks execs bash usually, unless you've told it to launch something else instead. And there's also support for what's called creating a session leader. So init can also fork more inits if you have kind of multiple users logged in at the same time and they all have their own bash environments. Obviously, we want to separate them. So this custom init process is what actually is going to be the proxy in a way that's going to create all the processes that you're going to launch with bash.exe or with lxrun as needed. So let's talk a little bit deeper about that IPC mechanism, how exactly a Windows app can talk to a Linux app, or vice versa. Now, of course, since you've got sockets and files in this environment, this is kind of the standard documented way. You can use Unix sockets to have Unix applications talk to each other. But if you want to talk to Windows, very simply, you have sockets. You can set up a server on localhost. On the Windows side, you connect to the localhost service, and then these things can actually talk to each other. Similarly, since the file system is mapped and mounted, you can create a file on the Windows side, read it on the Linux side, write back into it on the Linux side, and read the answer on the Windows side. So sockets and files work, but that's not the internal IPC mechanism they use. This is kind of the external model that exists. And as a developer, this is what you're supposed to use. Internally, though, the more interesting IPC is this bus IPC model, which for legacy reasons is still called ADSS IPC, which came from the name Android subsystem. And I'll share a little bit later kind of where that name came from and why it says Android in there. So basically, this allows you to create a named server, register it, have someone connect to that named server, and then basically you can use read and write calls on the Linux side or on the Windows side to basically send and receive messages. Or you can use ioctls on the Windows side or on the Linux side to marshal and unmarshal certain kinds of data. Now, on the Windows side, to register a server, you need to send an ioctl. And only the Linux manager service can send this ioctl. So it's normally locked down. However, the COM interface that it creates has a method called register ADSS bus server. And if you're admin, you can register a bus server. Once you register the bus server, you actually get back in your process a handle to the server port, and then you can start sending ioctls on the server port. So for example, you can send wait for connection, and now you're going to block waiting for Linux process to connect to you. The Linux side would then open /dev lxss. They have to be root in order to be able to do that. Then it can send an ioctl to connect to you. And now by using read and writes, the Linux side has a file descriptor. On the Windows side, you have a file handle, and you can talk to each other. The key is that right now, by default, only the init daemon can actually talk to a Windows process. So opening /dev lxss is only allowed if you're init, if your PID is 1. However, if you go into registry, there's a parameters key called root ADSS bus access. And if you set that to 1, then anyone who's root in the Linux environment can use this IPC mechanism as well. And of course, then it gets interesting because you can have custom Linux apps, which once this change has been done in your registry, can talk to custom Windows apps. So there's also marshalling. So what can you marshal and unmarshal? You can take a PID on the Linux side, marshal it, and the Windows side will get a process handle, right? Because ultimately Linux PID is going to be a Pico process. So if the Windows side wants to have a handle to the Pico process, it can be marshaled as a PID. You can marshal console handles. So console handles are how when you launch bash.exe, you get a Windows console, but then the actual bash Linux app has a standard in and standard out. That's a marshaled console handle. You can marshal pipe handles as well. And this is actually really interesting, and I've tried it out. Basically lets you create a pipe on the Windows side that shows up as a file descriptor on the Linux side, and then by using pipe APIs on Windows and using a read and write on Linux, you can actually just do standard pipes. So this actually allows piping from Windows to Linux, but they don't actually expose this. Like today, if you run bash and you pipe it with something else, it won't actually pipe. But obviously the implementation is in there. And finally, you can also marshal tokens. So Windows app can create a token or get an anonymous token and then send it to the other side. And when it gets unmarshaled, when that process then forks, it's going to fork with the new token. And there's some interesting things there that James Forshaw's going to be honest. I'm sure he'll look into that. So there's some ioctls to kind of do that kind of marshal and unmarshalling. You also get some data exchange APIs. So the data exchange APIs, one side can create or register a shared memory section, and the other side can see it. One side, the Windows side, can create an event object that the other side can signal, or the Linux side can have an event object that gets signaled and then the Windows side wakes up. So you can use epoll or select or wait for a single object to then kind of do data exchange beyond just messages. And a Linux app can actually share part of its address space with an NT app, and then the NT app can map it. So you can't do vice versa yet. I'm sure they kind of thought about why that might be a bad idea. But a Linux app can essentially make the whole address space that it has visible to a Windows app, and then Windows app can map it and modify it for read-write access only. So thankfully, there's no way to do that with execute access unless there's a flaw or a vulnerability. So that's kind of the interfaces that exist. We have this IPC mechanism, you have the system calls, and then you have the file system. So we'll talk a little bit about some of the security issues that kind of arose as I was looking through all this. So initially, this whole idea of a Pico process actually came from something called Project Astoria. And actually, it was something from more than a year ago. And it was supposed to be an Android runtime that lets you run Android applications on Windows 10 mobile. And so all of this was not for Bash. It was so you can run, Angry Birds or whatever Android app doesn't exist on a Windows phone. When this was in preview builds, the only way you can kind of play with this was actually either have a Windows phone, so the 5 people in the world who have that, or have the Windows mobile emulator. So when I did my initial research, it was against the Windows mobile emulator. However, when the final version came out, they just completely got rid of all of this code. So it just disappeared. There's no more Project Astoria, no more Android support. So that was kind of disappointing. In the anniversary of the previews, though, which final build came out yesterday, they replaced this ADSS driver with an LXSS driver. And so Project Astoria was gone, and now they basically re-implemented the original Project subsystem, right? Because Windows, from the beginning, could run Linux applications. Just they had to recompile the SPE, and then they got rid of it and brought it back, and got rid of it and brought it back. So now it's back again, except it runs ELF files. And instead of running the Android AOSP, now it runs Ubuntu 14. And then they added a lot more support for desktop apps instead of just mobile apps, and they got rid of things like the frame buffer, or things like the Android debugging bus, ADB, and they made it a Linux subsystem instead of an Android subsystem. And so when I first saw this on the Insider Preview, one of the interesting things was, for example, processes were invisible in Task Manager. So you spawn up a bash prompt and man or tail or less, and you wouldn't see nothing in Task Manager. In Process Hacker and Resmon, you would see them, but not TaskMan. The documented kernel API that security vendors have, which gives them notifications that processes are being created, you didn't get a notification for Pico processing Pico threads. They're basically invisible to you. The libraries and the processes that are being created and mapped, they're not mapped as sec image. They're not mapped as image section objects, so you don't actually get image load notification callbacks. So this bypasses app locker when you launch a Linux app, for example. If you whitelist bash.exe, or if you whitelist a bash launcher, you automatically whitelist any ELF binary. And then any file access and any network access appears like it's coming from the kernel, right? Because LX core is actually doing the access. It will be pointing to the PID and the TID in user mode that's actually doing this, the actual Pico process, but the previous mode will be set to kernel. So you might trust this I/O because it looks like it's coming from the kernel, unless you look deeper and you see that's coming from user mode. And there's an API that vendors can use to get the name of a process. For a Pico process, this return null. So if you somehow saw some malware doing something in a Linux environment, you wanted to get its name, you got back null. And then all of this was hidden behind this developer mode and feature installation that basically said if you want to use any of these features, you have to be in developer mode. But the truth was that LX Core was installed by default. And LXSS Manager, which did the actual checks, well, it provided a COM interface, yes, which went through the checks, but the driver itself allowed any admin to talk to it. So basically, because LX Core was there by default, regardless of whether developer mode was on or not, anyone could just talk to the driver and create instances. So back in February, before this was even announced, I tweeted out this picture where I had this thing called PicoMe, a random Windows executable, without actually even having installed WSL because it didn't even exist. And there was LX Core going ahead and launching a process and validating an ELF header. And that's when Microsoft reached out to me and said, stop tweeting about this. So, because they didn't want the first announcement for WSL to be, here's some random ELF malware. Few other problems is that all the handles these Pico processes create end up being kernel handles. So if you look at the handle table with any tools, you don't see anything. You could also inject Win32 threads in these Pico processes. You could change the context of a Pico process. You could modify the memory of a Pico process. So basically, there was no layer of protection between a Windows app running as Alex and a Pico app running as Alex, even though they're very different things. And the weirdest thing was the ability to inject an NT thread inside of a Pico process. So the Pico threads were talking to the Linux kernel, the Windows threads were talking to the Windows kernel. And then you had fun stuff where the Windows kernel allows you to map addresses below 64K if you're a Linux app for compatibility. The Windows kernel doesn't let you do that if you're a Windows app, because that's often used for null pointer exploitation. So I could use the Linux thread to map the memory I normally don't have access to as a Windows thread, then use the Windows thread to then launch an exploit that normally would be mitigated against. So that was an issue as well. And then finally, the fact that there's no PEB, no TEB, the whole thing is ELF. How much security software today is ready to like hash an L file and understand what an L file is and extract feature vectors from an L file and run indicators of compromise from an L file? Now, if you have a Linux product, sure, but on Windows, most products kind of don't bring them with them. So this really made me think that this is really dangerous if this ships out in this state. So I reached out to Microsoft and basically decided to help address some of these issues, give them some suggestions, bring them up ahead of time. So hopefully by today, these issues would be past issues and not current issues. So let's see that today. So today, all these processes show up in Task Manager. SC locate process image name, returns the name, so it doesn't return null anymore. The driver has a special ACL, which only allows protected processes to touch it, so you need to be signed by Microsoft to be able to talk to it. Developer mode is now correctly enforced. You see all the network I/O and netstat. You see all the file I/O and resource monitor, and you can no longer open a handle to a Pico process from a Windows process, except for very limited rights. I can't inject memory, inject a thread, mess with a Pico process from a Windows process in any way. So pretty much everything that kind of went out has the big issues, they fixed those. Yet there are some things that remain by design, right? The first thing that's there to realize is that file handles are still going to be kernel handles. So if you have a Linux process that actually opens a Windows file, you're not gonna see that in the handle table of the actual process. If you look at the handle tables of in Process Hacker of absolutely any Pico process at all, just to show you one here, it's completely empty, right? But this isn't really empty. It's actually accessing things. Unfortunately, it's accessing them as part of the kernel process. So I've got tail here, which has an index.html file opened. And look who apparently has index.html opened. It's the system process, right? Because it's actually a kernel handle, not a user mode handle. Now, the I/O, you would see that as being associated to the user mode process, but obviously the handle would be owned by someone else. And there's no symbols for any of this stuff. And again, it's all ELF, right? So if you have an AV software on Windows, how does it know about ELF files? You also have a big attack surface issue, right? 216 more system calls, 800 kilobytes of additional attack surface, things that have full network access, now within firewall rules, yes. Things that have full disk access within token rules, yes. But basically, you could write ransomware, which basically runs as a user account, encrypts all your files, and then runs in an environment that most endpoint software is not going to be able to react to. And then BSODs have been found. I mean, this thing crashed. There was a null pointer dereference, there was an invalid pointer dereference at some point, and these things were not found by fuzzers or by security researchers. They were found by users trying to use the environment during a preview. So this thing was crashing during a preview builds by people trying to use it. Who knows if people actually try to fuzz it and look at it. So thankfully, the IPC interfaces are locked down, but that might change in the future. So if you're writing endpoint software, if you're just a sysadmin, I'll finish with kind of some key things here, which is, first of all, you don't get any notifications for these threads or these processes. Now, there's an undocumented API that does give you those notifications, but it's not documented, so you're not supposed to use it. If you do use it, then you're going to know about the Pico processes. But they have no NTDLL, no PEB, no TEB, no shared user data, no API set, no PE file. So is your software going to be able to handle a process that has none of those things? Especially because there's no API to tell you if something is or isn't a Pico process. So if you try to touch the PEB, you'll just crash unless you check if it's null or not. Because these things aren't DLLs, your image load notifications don't get any callbacks. So you don't get any callback for NTDLL, you don't get a callback from the executable, because these things are not portable executables. They're ELF files. So you can see in Process Hacker and forensically, like if I look at man in the modules, I can actually see all the SO files and the man executable itself, but they're not mapped as images, they're mapped as data. So forensically, you can see them as ELF files, basically, as memory mapped files, but you won't get any callbacks in your load image notification to tell you that they've been loaded. And if you have a file system mini filter or a network mini filter, you will get the notifications for any file I/O. It will correctly point you to the Pico process that's doing this, but because you don't know it's a Pico process, because there's no API to know that, you might crash if you try to read its PEB or try to touch NTDL, so you kind of have to guard yourself and now realize there's these processes that don't have the normal data that it normally have. And on top of that, if you've been basically using like a correlation of knowing what PIDs you've created and what PIDs have been created and what TIDs have been created, because you never got a notification that this process was created, you're not actually going to know what this process is, right? You're going to look up, is this a real process or not? And if you tracked all creations, you would have never seen this process, so you don't actually know that a creation happened. And I have a quick screenshot here from Process Monitor. Here's Process Monitor seeing me read the index.html file. So you can see it's very useful information about this process. And if I look at a stack of this index.html file, it's just showing me Linux opening the file, right? There's nothing in user mode here whatsoever. And even in the main Process Monitor UI, here's who created the file. An empty process with nothing associated with it. So this is not really great, right? This is pretty scary if the bad guys start using some of this stuff. So I'll skip all these and just conclude with basically saying that, Microsoft, you have to appreciate, they took the time to basically fix all the issues I brought up. They addressed every single one of the main issues that were not kind of things that were done by implementation design. At the same time, they addressed all the user requests from people that wanted more and more features. They started blog posts, they started videos. So they've done a lot of good work to kind of demonstrate what the system is all about. But there's nothing for AV vendors. There's nothing for security vendors, right? The API to know about Pico processes is undocumented. There's no API to know if you have a Pico process that you're touching. And most security software probably is not aware that things can have a null PEB, that there might not be a shared user data, that there won't be a notification for NTDLL. So they might deadlock, they might assert, they might crash as they start encountering these Pico processes. And more importantly, how many vendors today have an ELF parser in their Windows binary, right? Who parses ELF files on Windows? Some AV companies do, but a lot of them, especially a lot of new startups and cyber startups, they probably never assumed they'd have to worry about ELF files on a Windows machine. So my worry is that they're gonna hack their way around, use undocumented structures, basically figure out a way to protect systems because there's no official guidance from anyone. So that really has to change, otherwise things are gonna be pretty dangerous in the Linux world. So with that being said, I want to thank a bunch of people, especially Angel Albertini. He's the one who actually created this the really cool picture at the beginning. So with the little evil Linux thing hiding inside. So thanks to Ange, and thanks to everyone else who helped with this. Microsoft blogs on the WSL talk about some of this stuff as well. There's a GitHub page where you can see all the issues that people have been submitting, and I will post on GitHub videos of the demos as well as the source code that I used, so you don't actually miss out on that. So you have my presentation slides and a video. I will publish that on my UNESCO007 GitHub. You can email me, pretty easy to find online. So that's that. So thanks a lot. Sorry I ran a little bit late. Hope you liked it. If you have any questions, again, there's a coffee break, so you can probably reach out to me after since I'm over time. But thank you very, very much, and enjoy Black Hat. Thank you.